There's a chip in your phone more complex than anything humans have ever built. It costs $12,000 to make. You bought it for 50 bucks. And the company that made it controls the entire world economy. Pull out your phone right now. Look at it. That tiny device you're holding has more computing power than the supercomputers that put humans on the moon. It is billions of transistors smaller than a virus. It processes trillions of calculations per second. It can do things that seemed like science fiction 20 years ago. And somehow, it gets cheaper every single year. Not more expensive, cheaper. A phone that would have cost $2,000 5 years ago costs $600 today, with better specs. How is that possible? How does technology get more advanced and less expensive at the same time? The answer is semiconductors. Tiny chips made of silicon that power everything electronic in your life. And behind those chips is a business so complex, so capital intensive, and so geopolitically important that most people have no idea it exists. Today, we're going deep into the semiconductor industry. We're talking about how chips are made, why they keep getting cheaper, who makes them, how much money is involved, and why this industry might be the most important business on Earth. Because the semiconductor industry doesn't just power your phone, it powers modern civilization. And it's all controlled by a handful of companies you've probably never heard of. Get ready, this is going to blow your mind. Let me start with a number that'll set the stage. TSMC, Taiwan Semiconductor Manufacturing Company. You've probably never heard of them unless you're into tech. But they make the chips that go into your iPhone, your laptop, your car, your TV, everything. They're the most important company you've never heard of. And they're worth over $500 billion. That's more than Walmart, more than Visa, more than most companies you interact with daily. TSMC doesn't make products you buy. They make the chips that go into products you buy. They're what's called a foundry. Other companies design chips. TSMC manufactures them. Apple designs the chip for the iPhone. TSMC makes it. NVIDIA designs graphics cards. TSMC makes them. AMD, Qualcomm, MediaTek, hundreds of companies design chips. TSMC makes most of them. Why does one company in Taiwan make so many of the world's most advanced chips? Because making semiconductors is insanely difficult and expensive. So difficult that only a handful of companies in the world can do it at the cutting edge. And TSMC is the best. Let's talk about how chips are actually made. Because understanding the process will help you understand why the economics are so crazy. A semiconductor chip starts as sand, pure silicon sand. This sand is refined into polysilicon, then grown into a crystal ingot. This ingot is sliced into thin wafers, about the thickness of a credit card and about 12 inches in diameter. These wafers are the canvas on which chips are built. Next comes photolithography. This is where the magic happens. The wafer is coated with a light-sensitive material called photoresist. Then a pattern is projected onto the wafer using extremely precise light. This light is so precise that it can create features smaller than the wavelength of visible light. They use ultraviolet light, specifically extreme ultraviolet or EUV light, with a wavelength of 13.5 nanometers. To give you perspective, a human hair is about 80,000 nanometers wide. Modern chips have features that are 3 to 5 nanometers wide. That's about the size of a few atoms. We're literally building structures at near atomic scale. The precision required is beyond anything else humans manufacture. After the light exposes the pattern, the wafer is developed like old photographic film. The exposed areas are removed. Then the wafer is etched, depositing or removing material to create the layers of the chip. This process is repeated dozens of times, building up the chip layer by layer. Each chip has billions of transistors arranged in complex patterns. The machines that do this cost over $150 million each one. A single EUV lithography machine from a company called ASML costs $150 million. ASML is a Dutch company that's the only manufacturer of these machines in the world. They make maybe 40 to 50 machines per year. and every cutting-edge chip factory needs multiple machines. Building a chip fabrication plant, or fab, costs between $10 to $20 billion. 10 to 20 billion for one factory. These are the most expensive factories humans build outside of nuclear power plants. TSMC is currently building a fab in Arizona that will cost $40 billion. $40 billion for one factory. Why so expensive? Because the precision required demands incredibly advanced equipment. The fabs have to be cleaner than hospital operating rooms. A single speck of dust can ruin a chip. So the air is constantly filtered, workers wear full-body suits, everything is controlled to ridiculous precision. Temperature, humidity, vibration, all of it can affect chip production. The fabs also use massive amounts of water and electricity. A single fab can use millions of gallons of water per day for cooling and cleaning. They use as much electricity as a small city. The utility costs alone are staggering. So here's the economics. It costs 10 to 20 billion to build a fab. Each fab can produce maybe 100 to 200,000 wafers per year. Depending on the technology, each wafer can have hundreds or thousands of chips on it depending on chip size. So a fab might produce tens of millions of chips per year. If you spread the construction cost over the fab's lifetime, maybe 10 years, that's 1 to 2 billion per year in capital costs. Add in operating costs, labor, materials, and you're looking at maybe 3 to 5 billion per year to run a cutting-edge fab. Divide that by the number of chips produced, and each chip costs maybe $50 to a few $100 to manufacture depending on size and complexity. But here's where it gets interesting. Once a fab is built and running, the marginal cost of producing one more chip is relatively low. Most of the cost is fixed. The building, the equipment, those are sunk costs. Making one more wafer doesn't cost that much extra. So as production volume increases, the per chip cost decreases dramatically. This is why semiconductor manufacturing has such strong economies of scale. The companies that can afford to build the most advanced fabs and run them at high volume can make chips cheaper than anyone else. This creates a natural monopoly tendency. The biggest players can undercut smaller competitors because their per chip costs are lower. TSMC understood this early. They invested heavily in building the most advanced fabs. They ran them at maximum capacity. This allowed them to offer lower prices than competitors while maintaining profitability. Smaller competitors couldn't keep up. They fell behind technologically or went out of business. Now TSMC has over 50% market share in chip manufacturing. They're a quasi-monopoly. The other major players are Samsung and Intel. Samsung makes chips for themselves and others. They're second to TSMC in advanced manufacturing. Intel used to be the leader, but fell behind in the last decade. They're trying to catch up by building new fabs. But it's expensive and they've struggled. The Chinese government is trying to build a domestic semiconductor industry. They're investing hundreds of billions in fabs and chip companies, but they're years behind TSMC and Samsung technologically. Making cutting-edge chips requires not just money but expertise and equipment that takes decades to develop. Now let's talk about Moore's Law, because this is why your phone gets cheaper every year. Moore's Law, named after Intel founder Gordon Moore, observes that the number of transistors on a chip doubles approximately every 2 years. This doubling means chips get more powerful over time. Twice as many transistors means twice the computing power, roughly. But here's the key insight. As transistors get smaller, you can fit more on the same size chip. And making chips is mostly about the cost of the fab and the wafer. If you can fit twice as many transistors on the same wafer, you're getting twice the performance for approximately the same manufacturing cost. This is why chips get more powerful and cheaper simultaneously. In 1971, Intel's first microprocessor had about 2,300 transistors. It cost $200 in today's money. That's about 9 cents per transistor. Today's Apple A17 chip and the iPhone has about 19 billion transistors. The chip costs maybe $50 to manufacture. That's about 0.000003 cents per transistor. Transistors have become millions of times cheaper over 50 years. This exponential improvement in price performance is unprecedented in any other industry. Imagine if cars followed the same trajectory. A car that cost $20,000 in 1971 would cost about 1 cent today and have the performance of a Ferrari. That's the scale of improvement in semiconductors. But Moore's law is slowing down as transistors approach atomic scale. We're hitting physical limits. You can't make transistors smaller than atoms. The current cutting edge is 3 nanometer features. The next generation will be to nanometers. After that, maybe 1 point for nanometers. But we're running out of room to shrink. This is causing a shift in the industry. Instead of just making transistors smaller, companies are finding other ways to improve chips. They're stacking transistors vertically instead of just horizontally. They're using new materials beyond silicon. They're designing chips more efficiently. They're using chiplets where multiple smaller chips are connected together to function as one larger chip. These innovations keep performance improving, but not at the same exponential rate. Some analysts predict Moore's law will effectively end in the next decade. When that happens, chip performance will still improve, but more slowly, and prices might stop declining as dramatically. Let's talk about the business models of chip companies, because there are several different types. First, there are integrated device manufacturers or IDMs. These companies design and manufacture their own chips. Intel is the classic example. They design their processors and make them in their own fabs. Samsung is another IDM. They design and make their own chips. Then there are fabless companies. These companies design chips but don't manufacture them. They outsource manufacturing to foundries like TSMC. Apple is fabless. They design the chips for iPhones and iPads, but TSMC makes them. Nvidia is fabless. They design graphics cards and AI chips. TSMC makes them. Qualcomm is fabless. They design the chips for most Android phones. TSMC makes them. Being fabless makes sense for many companies because building fabs is so expensive. Why invest $20 billion in a fab when you can pay TSMC to make your chips? You can focus on design and let specialists handle manufacturing. This is why the fabless model has become dominant. Then there are pure-play foundries like TSMC. They don't design chips. They just manufacture chips that other companies design. This allows them to serve many customers and achieve high utilization of their fabs. It's a great business model. TSMC's profit margins are around 40%. 40%. That's insane for manufacturing. But it's possible because of the economies of scale and the limited competition. There are also equipment manufacturers, companies like ASML, Applied Materials, Lam Research, and Tokyo Electron make the machines used in chip fabs. These companies are incredibly profitable because their equipment is essential and there are few alternatives. ASML is the only company that makes EUV lithography machines. They have a monopoly on the most critical tool for making advanced chips. Their profit margins are around 30%. The semiconductor industry is also incredibly cyclical. Demand for chips fluctuates based on the broader economy. When economies boom, people buy more electronics, so chip demand increases. When economies contract, demand drops, but chip fabs take years to build. So companies have to predict demand years in advance. If they guess wrong, they either have too much capacity, which means unused fabs losing money, or too little capacity, which means shortages and lost sales. We saw this during COVID. When the pandemic hit, chip demand cratered initially. Everyone thought the economy would tank, so chip companies cut production. But then demand exploded because people stuck at home bought computers and phones for remote work. Suddenly there was a global chip shortage. Cars couldn't be built because they lacked chips. Game consoles were unavailable. Prices spiked. The chip industry is now in a different phase. They overbuilt capacity in response to the shortage. Now there's too much capacity for some types of chips. Prices are falling. Some companies are cutting production. It's a boom-bust cycle that repeats every few years. Now, let's talk about why semiconductors are geopolitically critical. Because this isn't just about technology, it's about power. Whoever controls semiconductor production controls the modern economy. Everything digital requires chips. Your phone, your computer, your car, your weapon systems, your power grid, everything. And most advanced chips are made in Taiwan. TSMC makes over 90% of the world's most advanced chips. Taiwan is a small island that China claims as its territory. If China invaded Taiwan, or even blockaded it, global chip supply would be cut off. The world economy would collapse. No new phones, no new computers, no new cars. Military equipment would fail, as chips wore out without replacements. This is why the US is so committed to defending Taiwan. It's not just about democracy or international law. It's about semiconductors. Taiwan is strategically important to lose. The US has called semiconductors the oil of the 21st century. Whoever controls chip production has economic leverage over everyone else. The US dominated semiconductors for decades. Intel, Texas Instruments, Micron, and others were the leaders. But manufacturing shifted to Asia for cost reasons. TSMC and Samsung invested heavily while US companies fell behind in manufacturing. Now the US designs chips but depends on Asia to make them. This is a strategic vulnerability. The US government is trying to fix this. The CHIPS Act passed in 2022 allocated $52 billion in subsidies to bring chip manufacturing back to the US. TSMC is building fabs in Arizona. Samsung is building in Texas. Intel is building in Ohio and Arizona. The goal is to produce at least 20% of advanced chips domestically by 2030. But it's not easy. Building fabs in the US is more expensive than in Taiwan. Labor costs are higher, regulations are stricter, and there's not enough skilled workers. Taiwan has thousands of engineers trained in semiconductor manufacturing. The US has to rebuild that expertise. It'll take years and billions of dollars. China is in a similar position, but worse. They import most of their advanced chips. They're desperately trying to build domestic capacity. But the US has banned exports of chip-making equipment to China. This cripples China's ability to build cutting-edge fabs. They're stuck making older generation chips. They may be 5 to 10 years behind TSMC technologically. This is economic warfare. The US is using its control over chip equipment and chip design tools to prevent China from advancing. China is pouring hundreds of billions into circumventing these restrictions. It's a technological arms race with global implications. Let's talk about chip design, because manufacturing is only half the story. Designing a modern chip takes hundreds of engineers working for years. A chip like Apple's A17 or NVIDIA's latest graphics card required thousands of person-years of work to design. The designs are incredibly complex. Billions of transistors have to be arranged in patterns that maximize performance while minimizing power consumption and heat generation. Companies use sophisticated software called EDA tools, electronic design automation, to design chips. These tools are made by companies like Synopsys, Cadence, and Mentor Graphics. They're essential. You can't design modern chips without them. And these companies are mostly American. So the US controls a critical part of the chip supply chain even though manufacturing happens in Asia. The cost to design a cutting-edge chip is now over $500 million. $500 million just to design it, before manufacturing. This creates huge barriers to entry. Only large companies can afford to design the most advanced chips. This is why there are only a handful of companies making smartphone processors, graphics cards, or server chips. So here's the fundamental problem. The semiconductor industry has become incredibly concentrated. A handful of companies control each part of the supply chain. ASML is the only maker of EUV lithography machines. TSMC and Samsung make most advanced chips. Few companies make it as software. This concentration creates vulnerabilities. If any of these companies fails or gets disrupted, the entire global economy is affected. We saw this during COVID when chip shortages rippled through every industry. And it could get worse. A major earthquake in Taiwan could take TSMC offline for months or years. That would be catastrophic globally. There's also the geopolitical risk. If China invades Taiwan, it's not just a regional conflict. It's a global economic catastrophe. The US and China both know this. It creates a dangerous dynamic where military conflict over Taiwan has apocalyptic economic consequences. The industry is also incredibly expensive to enter. Building competitive fabs requires tens of billions of dollars and decades of expertise. This means new competitors can't easily emerge. The existing players have quasi-monopolies. They can charge high prices because customers have few alternatives. There's also the environmental cost. Chip manufacturing uses massive amounts of water, electricity, and chemicals. It produces toxic waste. As demand for chips grows, so does the environmental impact. Taiwan is already facing water shortages partly due to chip fabs. Arizona is questioning whether they have enough water for the TSMC fabs being built there. And then there's Moore's Law ending. For 50 years, chips got exponentially better and cheaper. This drove economic growth. It made new technologies possible. But if Moore's Law ends, that exponential improvement stops. Progress slows. Some economists worry this could slow overall economic growth. We've gotten used to technology getting better every year. What happens when it doesn't? Different approaches are being tried to address these issues. Geographic diversification is one. Instead of concentrating manufacturing in Taiwan, building fabs in multiple countries. The US, Europe, Japan, and others are all trying to build domestic chip industries. This reduces dependence on any one country, but is expensive and duplicates infrastructure. Some companies are exploring new materials beyond silicon, gallium nitride, silicon carbide, graphene, and other materials might allow chips to go beyond silicon's limitations. But these technologies are still early. It'll be years before they're commercially viable at scale. Three-dimensional chip stacking is another approach. Instead of making transistors smaller, stack multiple layers of chips on top of each other. This increases performance without shrinking transistors. Companies like AMD and Intel are already doing this. It's more complex to manufacture, but it works. Specialized chips are becoming more important instead of general-purpose processors. Companies are making chips optimized for specific tasks. AI chips, crypto mining chips, automotive chips. These specialized designs can be more efficient for their specific use case than general purpose chips. Some people think quantum computing will eventually replace semiconductors for certain applications. Quantum computers work completely differently from traditional computers. They could solve problems that are impossible for regular computers. But quantum computing is still extremely early. We're decades away from practical quantum computers if they're even possible. Others think we'll hit fundamental limits and technology progress will slow. We've had exponential improvement for 50 years. Maybe that era is ending and we enter a period of slower, incremental progress. This would be a major economic shift. We're at a critical moment in the semiconductor industry. For the first time in decades, the industry is fragmenting geographically due to geopolitical tensions. The globalized supply chain that made chips cheap is being replaced by regional supply chains, driven by national security concerns. This will make chips more expensive, duplicate fabs in multiple countries mean higher costs. Restrictions on chip sales to China mean lost economies of scale. The era of ever cheaper chips might be ending not because of technology limits, but because of politics. At the same time, demand for chips is exploding. AI requires massive computing power. Electric vehicles need far more chips than gas cars. The Internet of Things is putting chips in everything. Data centers are growing exponentially. All of this drives chip demand higher. But building new capacity takes years and costs billions. There's going to be a mismatch between supply and demand. This could mean higher prices, shortages, and rationing. It could slow the deployment of new technologies. It could become a bottleneck for economic growth. The companies and countries that control semiconductor production in the next decade will have enormous power. They'll determine which technologies get built and who gets access. This is why the US, China, Europe, and others are racing to build capacity. It's not just about economics. It's about strategic power in the 21st century. Your phone gets cheaper every year because of Moore's Law and the economics of semiconductor manufacturing. As transistors shrink, you can fit more on each chip as production scales up. The per-chip cost decreases. This creates exponential improvement in price performance that's unprecedented in any industry. But this is only possible because of an incredibly complex and expensive supply chain. Companies like ASML make machines that cost $150 million. Companies like TSMC build fabs that cost $20 billion. They use these to make chips with billions of transistors, each smaller than a virus. It's the most advanced manufacturing humans do. The industry is dominated by a handful of companies. TSMC makes most advanced chips. ASML makes the critical manufacturing equipment. A few companies make chip design software. This concentration creates efficiency, but also vulnerability. Any disruption affects everyone. The industry is also geopolitically critical. Most advanced chips are made in Taiwan. This gives Taiwan and TSMC enormous leverage. It also makes Taiwan a flashpoint for US-China tensions. Whoever controls chip production controls the modern economy. The US is trying to rebuild domestic chip manufacturing with the CHIPS Act, $52 billion in subsidies to build fabs in America. But it's expensive and will take years. Meanwhile, China is trying to build its own industry despite US restrictions. It's a technological Cold War playing out in semiconductors. The era of exponential improvement might be ending. Moore's Law is slowing as we hit physical limits. Geopolitical fragmentation is making chips more expensive. Demand is exploding while supply is constrained. The next decade could see chip shortages, higher prices, and slower technological progress for you. This means your phone might not get dramatically better every year like it used to. The magical doubling of performance every 2 years might stop. Technology progress might slow, and the cheap electronics you're used to might become more expensive. As the semiconductor industry restructures, the chip in your phone that costs $50 to you and $12,000 to make represents one of humanity's greatest technological achievements. Billions of transistors arranged with atomic precision to process trillions of calculations per second. It's only possible because of decades of exponential progress and massive industrial scale. That era might be ending, not because we can't make better chips, but because the geopolitics and economics of chip making are changing. The globalized supply chain that made chips cheap is fragmenting. The concentration that made chips advanced is becoming a strategic vulnerability. The semiconductor industry has been invisible to most people, but it's the foundation of modern life. Everything digital depends on it, and that industry is changing in ways that will affect everything: your phone, your car, your job, your country's security. All of it depends on those tiny chips, and the business behind them is the most important you've never heard of. The monopoly we expose next will make you realize who really controls what you see online.